All right. So now what I want to leave with you is the final chapter of our study, which relates to the study of efficient implementation of the DFT, and that is going to be called the fast Fourier transform. So an important aspect that I want you to look at are the properties of the DFT matrix. So here are some, so we are going to be looking at now chapter 9, the computation or efficient computation of the DFT. The title of the chapter 9 is efficient computation. Computation of the discrete Fourier transform, or in other words, this is the algorithm which is called the fast Fourier transform, and there are many fast Fourier transform algorithms. What we are going to be looking at is one of the most commonly used FFT algorithms. It's called, so FFT stands for fast Fourier transform, same as discrete Fourier transform, but computed in a very efficient manner. Okay, so the important to once again remind ourselves that when you are in the discrete time domain, okay, your signal can be either periodic or it could be finite length or aperiodic signal. Aperiodic. Okay. Now what we have is, for periodic signals, we have the discrete Fourier series representation. For finite length sequences, we have the discrete time Fourier transform. Okay. Now in the boundary between these two, okay, in between. So in other words, I have a finite length sequence, but I'm going to create a periodic repetition, and that produces for me a new representation which is in between. This is called DFT. Okay, it is a finite length sequence, it's a representation of a finite length sequence, but it relies very heavily on the periodic signal which has the properties which is DFS. Okay. And DFT has got a very efficient implementation. This is what we call as the fast Fourier transform. Okay, so where does fast Fourier transform fit in? It is basically where DFT fits in. Where does DFT fit in? It is in between DTFT and DFS. Okay. So what are some of the aspects to be reviewed? We can look at it very quickly. Okay, when you multiply two complex numbers, so we will look at a quick how to estimate computational complexity. Computational complexity. Okay, we are dealing with transform, which is basically the matrix has got all complex numbers. So when you are looking at one complex multiplication, okay, I'm going to use the short form 1 cm. Okay, and what does 1 cm typically represent? Multiplication of two complex numbers, a plus jb, c plus jd. Now I'm sure you are very familiar with the expansion. This will be equal to AC minus BD, that will be the real part, plus J times AD plus BC. That's the imaginary part. Okay, so what this happens is you get 4 multiplication, AC, BD, AD, BC. So this is actually equal to 4 multiplies, and there are 2 adds. AC and BD have to be subtracted, AD and BC might be, and addition subtraction we don't make a difference. So basically it's the same as 4 multiplies and 2 adds. So one complex multiplication is equal to 4 real multiplications plus 2 real additions. Similarly, one complex addition CA addition is equal to 1 CA. This is equal to A plus C plus J times B plus D. Basically, it's the same as 2 additions. Okay. So, what I want you to do is keep this as a reference. 1 CM complex multiplication is equal to 4 real multiplications plus 2 additions. 1 complex addition is equal to 2 real additions. So, this is a reference table that you can always come back and substitute from to get the actual number of computations. Okay. Our focus of the FFT is on reducing the number of computations. Okay, and we will find that significantly the computations are in complex multiplies. So this means our focus on reducing the number of complex multiplies, number of CMs. Okay, that's what is our tendency that we are going to do. Okay. Now, supposing you wanted to look at what is the computational complexity of the DFT. So, direct computation of the DFT. Okay, how does that you get the vector x is equal to d subscript n times x. Okay, row times column. How many elements in the row? N. How many elements in the column? N. So basically, what you will get is each DFT coefficient x of k will require what sort of computation? N complex multiplies, because there are n elements in the row, n elements in the column, n complex multiplies, and you're adding n terms. So basically there are n minus 1 additions, n minus 1 complex additions. Okay. Now, how many DFT coefficients are there? Total n DFT coefficients are there. So for entire DFT, okay, that means x of k all the way to x of 0 to x of n minus 1. The total number is whatever is here multiplied by n. So what we get is of the order of n squared complex multiplies plus n into n minus 1 complex additions. Okay, and you look at it in the context of the complex multiplies. So this is of the order, this O stands for order, that means it's some factor related to that, order of n squared. So if the size of your FFT increases, your complexity is going to increase as the square. So a 16-point DFT compared to a 32-point DFT will be a factor of 4. So basically the complexity grows as the square of the size of the DFT. Okay, so we write that down as an important observation. Complexity of the direct computation of DFT. Computation of DFT grows exponentially as n squared, of the order of n squared. Okay, and this is where a phenomenally important invention came up in 1965. 1965, two scientists at Bell Labs, their names were Cooley and Tukey. They came up with an algorithm which significantly reduced the computations. Algorithm for efficient computation. of the DFT. Computation of DFT. Again, you can read up the details. There are several very interesting articles in IEEE about the history of the FFT. Definitely, you should, I would encourage you to read that. Computation of the, basically they were computing the Fourier series, but that's the same as Fourier transform. So basically, we'll write, say they've came up with the efficient algorithm. So basically what they have done is the efficient computation of the DFT. Their basic idea, okay, what was introduced by Cooley and Tukey was the following. Okay, can we break a size n DFT into two n by 2 point DFTs? Okay, so an n point DFT. Okay, this will have order n squared. Can it be done as two n by 2 point DFTs? Okay, is it possible? And they showed that it is actually possible, and what we get here will be 2 times order of n by 2 squared. Okay, so this is 2 into order of n by 2 squared. So you can say that this is of the order of n squared by 2. Again, very, very loose terminology. So from n squared, you have reduced the complexity, or you expect to reduce the complexity to the order of n squared by 2. Now, actually, it is along these lines that we are developing, and we will show that it can actually produce a very, very significant reduction in terms of complexity. And here are some of the observations that were made by Cooley and Tukey, that basically they looked at the symmetries in the DFT matrix. Symmetries in D subscript n, in the matrix, in the DFT matrix D subscript n. Okay, so basically here are some of the symmetries. If you remember, we looked at 14 properties. Where is that? Was it here? Yeah, okay. Slide number 8. 14 properties where we derived a lot of the symmetries. So I'll just mention a few of these that you know we will use here as well. Okay, so when you have the following relationship, Wn k plus n by 2 times n. Okay, this will come in the computation. This is nothing but minus 1 raised to the power n Wn kn. And like that, there are many symmetries through conjugation, through you can verify through substitution. So what I would like you to do is verify that Wn n by 2 is minus 1, Wn raised to the power of n by 4 is minus j, then you get a j. So basically this slide captures for us all the symmetry properties that are there available to us. Using all of these symmetry properties, exploiting all symmetry properties. Okay, what can you reduce the complexity to? So if you have a FFT of length n, which is a power of 2, then the total computational complexity of the fast Fourier transform, algorithm is of the order of n by 2 log base 2 of n. This is the number of complex multiplications, and then you get n times logarithm base 2 of n of complex adds. Okay, and this is something that you should look at it very carefully and see. This is extremely significant. Okay, now just so that you get a feel for what this is. So a typical size FFT that we would normally do is of the order of 1024. Okay. Now from here, the original DFT algorithm was of the order of n squared. N squared for this this quantity is 10,48,576. That is n squared. On the other hand, if you had n log base 2 of n, basically that's the order of the multiplications and complex adds. This is equal to 10240, 10,240. So where is 10 lakhs, where is 10,000? Okay, so you can see that the complexity reduction is very, very significant when we do the FFT algorithm. Okay, so now how does the FFT algorithm get derived? What are some of the techniques that are used? And those are what we are going to be looking at in the last segment of our course. So suppose, let's assume that n is equal to a power of 2. So nu is an integer. So we are looking at 16, 32, 64, some power of 2. If it is not a power of 2, if the length of the sequence that you not have, we can always use 0 padding to make it a power of 2. Always use 0 padding if needed to get the correct length. So never have to say that I don't have a power of 2 length sequence. You can always add the number of. Okay. So the first step, the DFT expression is summation n is equal to 0 through n minus 1 x of n wn kn. This is the DFT computation. Now x of n, if you look at the samples, the even samples are x0, x2, x4 and so on. On the other hand, the odd samples will be x1, x3, x5 and so on. So you know what are odd samples, even samples. So these are the even samples. These are denoted by x of 2n, where n is equal to 0. You can substitute in x of 0, x of 2. These are the odd samples. They are obtained as x of 2n plus 1. Okay. Now, I'm going to split this summation into the terms which correspond to the even samples and the term which corresponds to the odd samples. Okay. So, what am I going to do? I'm going to say that I'm going to take the first summation, r is equal to 0 through n by 2 minus 1. If the total of n samples are there, it's a power of 2, so I can take n by 2. n by 2 is half the number of samples, 0 to n by 2 minus 1. All the even samples, x of 2r, w subscript n, k n. So basically we substitute k times 2r. Remember, n is in wherever there was n, we are substituting 2r. Okay, and what about the remaining terms? The remaining terms are all the odd terms. So we get the same number of coefficients and n by 2 coefficients, 0 to n by 2 minus 1, x of 2r plus 1, all the odd coefficients. Okay, and that's the same, that is the time index. So what we get is wn k times 2r plus 1. Okay, take a moment to make sure that you are able to see how we have split the computation into the even samples, the term corresponding to the even samples and the term corresponding to the odd samples. Okay, here are some important results. Wn raised to the power of k times 2r is the same as wn by 2 raised to the power k times r. Okay. Using this result, we then write down saying that x of k can be written in the following form. Purple for the first term, summation r equal to 0 through n by 2 minus 1 x of 2r. So I'm going to simplify this expression. Simplification, w of n by 2 k times r. Okay, and the second term is in green, r equal to 0 through n by 2 minus 1 x of 2r plus 1. Expand this becomes a scale factor which is wn times k, and then wn by 2 times kr. Okay, so this is a scale factor that does not depend on r, so we can write this as plus wn power k, the remaining terms summation r equal to 0 to n by 2 minus 1 x of 2r plus 1 wn by 2 kr. Okay, let me write the first term also. This is equal to, so x of k can be written in the following form: r equal to 0 through n by 2 minus 1 x of 2r wn by 2 kr. Okay, now you have these two expressions as the composite expression for the DFT computation. Now notice that the following very, very important aspect. The first quantity that you have here represents an n by 2 point DFT of the even samples. Okay, let's call that as g of k. So what is g of k? G of k is a n by 2 point DFT of the even samples of x of n. Even samples of x of n. So that is basically represented by x of 2r. Then we have the scale factor. This is a scale factor, multiplicative scale factor. And then we have another n by 2 point DFT which we will call as h of k. H of k is an n by 2 point DFT of the odd samples of x of n. Okay, so what did we do? We took the sequence, n point sequence, took the even samples, took the odd samples, and then we combined them, took n by 2 point DFTs, and then are able to combine. Now what is k in this case? K will go from 0, 1 all the way through n minus 1 because x of k is a length n sequence. G of k, what is the range of g of k? It will be 0, 1 all the way to n by 2 minus 1. Similarly, so for these samples, k is in the range, no, let me, okay, let me make sure that we get this correctly. Okay, for g of k and for h of k, okay, the k is in the range 0 to n by 2 minus 1. When it goes outside of n by 2 minus n by 2, then you do modulo n by 2. So basically you can get the expression for x of k from the two n by 2 point DFTs. So the original question that we asked, can we reduce an n by n point DFT to two n by 2 point DFTs? The answer is yes. And that's exactly what we have shown. And what we have shown is that it can be reduced to two n by 2 point DFTs, which can then be combined using a scale factor. Okay. So, so what is the computational complexity of the new operation? Okay, so let's write that down. X of k is equal to g of k plus wn raised to the power k of h of k. Okay, and let us say that you are doing a direct implementation of the n by 2 point DFTs. Computation or complexity of an n by 2 point DFT, it will be of the order of n by 2 squared complex multiplies, right? That will be the total number, plus n by 2 into n by 2 minus 1 complex additions. Now remember that there are two of them. So this whole thing has to be multiplied by 2. Why am I multiplying by 2? Because I have to compute for g of k and h of k. Okay, and remember that I also have to perform one more operation which is in the combining g of k. So combining g of k and h of k. What does that require? Each of these, there are k terms, n by 2 terms. They're going to be multiplications by a complex number, and this will require n complex multiplies and then n complex additions plus n complex additions. Okay, so total complexity when after we have reduced it to 2 n by 2 point DFTs is given approximately, you can just verify, is n squared by 2, n squared by 4 into 2 plus n complex multiplies plus n squared is of the order of n squared by 2 complex additions. Okay, so basically you can verify that this is the complexity. Okay, and now is this better than n squared plus n squared, right? The original complexity was n squared complex multiplies and n into n minus 1 complex additions. Now you can verify that this will be always lower than direct computation of n point DFT. You can substitute any value, n equal to 4, n equal to 8, whatever you can substitute, and then you can verify computation of the n point DFT. Okay, for any n greater than 2. So there is always an advantage to split it in this fashion as we have shown.